When seeking a 700 amp DC single pole contactor suitable for switching 700 amps at 270 volts DC, several manufacturers and distributors can be considered. The coil voltage is variable and doesn't significantly limit the selection process. Several manufacturers produce suitable contactors. These include Eaton, Schneider Electric, AB, and Siemens. Eaton offers the PK-Zone series contactors. Schneider Electric provides the T-Sys D-series contactors. ABB features AF contactors. Siemens manufactures Series 3 RT contactors. These manufacturers have established reputations for quality and reliability in electrical components. Distributors are another avenue for sourcing these contactors. Key distributors include Grainger, ESCO, Allied Electronics, DigiKey, and Newark. Grainger is a large industrial supplier. ESCO specializes in electrical and HVAC components. Allied Electronics offers a wide range of electronic and electrical parts. DigiKey focuses on electronic components. Newark provides a broad selection of electronic components and tools. These distributors offer convenient access to various brands and models. Specific model numbers to consider from each manufacturer include the following. Eaton offers the PK-Zone -700-1. Schneider Electric provides the Elcon F700. ABB features the F96-30-7. Siemens manufactures the 3RT1075-6P0. These model numbers are examples and may vary based on specific requirements and availability. The key specifications for the contactor are as follows. Firstly, the pole count should be 1. Secondly, the current rating must be 700 amps. Thirdly, the voltage rating should be 270 volts DC. Fourthly, the coil voltage is variable. For example, 24 volts DC or 120 volts AC. Additional considerations when selecting a contactor include several factors. Firstly, ensure the contactor is compatible with the specific application requirement. Consider factors such as the type of load being switched, the frequency of switching, and the environmental conditions. Secondly, evaluate the contactor's life expectancy and maintenance needs. Consider the number of expected switching cycles and the required maintenance schedule to ensure long-term reliability. Thirdly, check the availability of accessories such as auxiliary contacts, surge suppressors, and terminal blocks. These accessories can enhance the functionality and protection of the contactor. Fourthly, consult with the manufacturer or distributor for technical assistance. They can provide valuable insights and guidance on selecting the most appropriate contactor for the application. When evaluating the contactor's compatibility with the application requirements, consider the following points. Determine the type of load being switched, whether it is resistive, inductive, or capacitive. Each type of load presents different challenges for contactor operation. Consider the inrush current associated with the load. Inductive loads, in particular, can generate high inrush currents that can stress the contactor contacts. Ensure the contactor is rated to handle these inrush currents. Assess the frequency of switching. Frequent switching can accelerate wear and tear on the contactor contacts. Select a contactor with a suitable duty cycle rating. Consider the environmental conditions in which the contactor will be operating. Factors such as temperature, humidity, and altitude can affect the contactor's performance. Choose a contactor that is rated for the specific environmental conditions. When evaluating the contactor's life expectancy and maintenance needs, consider the following points. Determine the expected number of switching cycles over the contactor's lifespan. Select a contactor with a mechanical and electrical life rating that meets or exceeds the expected number of cycles. Review the manufacturer's recommended maintenance schedule. Regular inspection and maintenance can help to prolong the contactor's life and prevent unexpected failures. Consider the cost and availability of spare parts. Ensure that spare parts are readily available and reasonably priced to minimize downtime in the event of a failure. When checking the availability of accessories, consider the following points. Auxiliary contacts can provide additional control and monitoring capabilities. Surge suppressors can protect the contactor from voltage transients. Terminal blocks can simplify wiring and connections. Ensure that the accessories are compatible with the contactor and meet the application requirements. When consulting with the manufacturer or distributor for technical assistance, be prepared to provide detailed information about the application. This information should include the type of load being switched, the voltage and current requirements, the frequency of switching, and the environmental conditions. The manufacturer or distributor can use this information to recommend the most appropriate contactor for the application. When selecting a contactor, it is important to consider safety. Ensure that the contactor is properly installed and grounded. Follow all applicable safety codes and regulations. Use appropriate personal protective equipment when working with electrical equipment. Regularly inspect the contactor for signs of wear or damage. Replace the contactor if it is damaged or malfunctioning. A 700 amp DC single pole contactor is a significant electrical component and should be selected and installed with care. By following these guidelines, you can ensure that you select the right contactor for the application and that it operates safely and reliably. When considering the variable coil voltage options for the contactor, it's important to understand the implications of each voltage choice. Common coil voltage options include 24 volts DC, 120 volts AC, 240 volts AC, and 480 volts AC. The selection of the coil voltage depends on the available control voltage source and the control circuit design. 24 volts DC is a common choice for control circuits due to its safety and compatibility with electronic control systems. It is often used in industrial automation and programmable logic controller or PLC applications. 120 volts AC is a common choice for general-purpose control circuits. It is readily available in most industrial and commercial facilities. 240 volts AC and 480 volts AC are typically used in larger industrial applications where higher voltage control circuits are required. When selecting the coil voltage, consider the following factors. Firstly, the availability of a suitable control voltage source. Choose a coil voltage that matches the available control voltage source to avoid the need for voltage conversion. Secondly, the control circuit design. Consider the voltage requirements of other components in the control circuit, such as relays, switches, and sensors. Thirdly, the safety requirements. Select a coil voltage that meets the applicable safety codes and regulations. It is important to note that the coil voltage does not affect the contactor's ability to switch the 700 amp to 270 volts DC load. The coil voltage only controls the operation of the contactor's internal mechanism. The contactor's contacts are responsible for switching the load current and voltage. In addition to the coil voltage, it is also important to consider the coil's power consumption. The coil's power consumption can affect the overall energy efficiency of the control system. Select a contactor with a low power consumption coil to minimize energy waste. Some contactors are equipped with economizer circuits that reduce the coil's power consumption after the contactor has been energized. These economizer circuits can significantly improve energy efficiency. When selecting a contactor with a variable coil voltage option, it is important to verify that the contactor is compatible with a specific voltage range. Some contactors may only be compatible with a limited range of coil voltages. Consult the manufacturer's specifications to ensure compatibility. In summary, when selecting a 700 amp DC single pole contactor, consider the manufacturer, distributor, model number, specifications, and additional considerations discussed earlier. Pay attention to the coil voltage options and select a voltage that is compatible with the available control voltage source and the control circuit design. By carefully considering these factors, you can ensure that you select the right contactor for your application. The importance of the correct interrupting rating for the contactor being selected cannot be overstated. The interrupting rating, expressed in amps, represents the maximum fault current that the contactor can safely interrupt without sustaining damage or creating a hazardous condition. Selecting a contactor with an inadequate interrupting rating can lead to catastrophic failure, posing significant safety risks to personnel and equipment. To determine the appropriate interrupting rating, a thorough short-circuit study must be performed. This study analyzes the electrical system to determine the maximum available fault current at the point where the contactor will be installed. The available fault current is influenced by factors such as the utility's supply capacity, transformer impedance, and conductor size and length. The short-circuit study should be conducted by a qualified electrical engineer or technician. The results of the study will provide the necessary information to select a contactor with an interrupting rating that meets or exceeds the available fault current. It is crucial to consult the manufacturer's datasheets to verify the interrupting rating of the contactor. The datasheets will specify the interrupting rating for various voltage levels and fault current conditions. The interrupting rating is typically expressed in symmetrical amps. In addition to the interrupting rating, it is also important to consider the contactor's withstand rating. The withstand rating, also expressed in amps, represents the maximum fault current that the contactor can withstand for a short period of time without sustaining damage. The withstand rating is typically higher than the interrupting rating. The withstand rating is important for applications where the contactor may be subjected to high fault currents for a brief duration. For example, in motor starting applications, the contactor may experience a high inrush current for a few cycles when the motor is started. The contactor's withstand rating must be sufficient to handle these inrush currents. When selecting a contactor, it is always advisable to err on the side of caution and choose a contactor with an interrupting rating and withstand rating that are higher than the calculated values. This provides a safety margin and ensures that the contactor will be able to handle unexpected fault current conditions. It is also important to consider the coordination of the contactor with other protective devices in the electrical system, such as fuses and circuit breakers. Coordination ensures that the protective devices will operate in a coordinated manner to isolate the fault and minimize the impact on the rest of the system. The coordination study should be conducted by a qualified electrical engineer or technician. The results of the study will provide the necessary information to select protective devices that are properly coordinated with the contactor. Proper coordination can prevent nuisance tripping and ensure that the electrical system is protected from damage. In summary, the interrupting rating and withstand rating are critical parameters to consider when selecting a 700 amp DC single-pole contactor. A thorough short-circuit study must be performed to determine the maximum available fault current at the point of installation. The contactor must be selected with an interrupting rating and withstand rating that meet or exceed the calculated values. Coordination with other protective devices is also essential to ensure proper system protection. The altitude at which the contactor will be operating can also affect its performance. At higher altitudes, the air is thinner, which can reduce the contactor's ability to dissipate heat. This can lead to overheating and premature failure. To compensate for the effects of altitude, it may be necessary to derate the contactor's current rating. Derating involves reducing the contactor's maximum allowable current to account for the reduced cooling capacity at higher altitudes. The manufacturer's data sheets will provide derating factors for various altitudes. The derating factor is typically expressed as a percentage. For example, a derating factor of 90% means that the contactor's current rating should be reduced by 10%. To determine the appropriate derating factor, consult the manufacturer's data sheets and the applicable electrical codes. The electrical codes will specify the requirements for derating electrical equipment at higher altitudes. It is also important to consider the ambient temperature in which the contactor will be operating. The ambient temperature is the temperature of the air surrounding the contactor. High ambient temperatures can also reduce the contactor's ability to dissipate heat. To compensate for the effects of ambient temperature, it may be necessary to derate the contactor's current rating. The manufacturer's data sheets will provide derating factors for various ambient temperatures. The derating factor is typically expressed as a percentage. For example, a derating factor of 90% means that the contactor's current rating should be reduced by 10%. To determine the appropriate derating factor, consult the manufacturer's data sheets and the applicable electrical codes. The electrical codes will specify the requirements for derating electrical equipment at higher ambient temperatures. In addition to directing the contactor's current rating, it may also be necessary to provide additional cooling. Additional cooling can be provided by using fans or air conditioners. The amount of additional cooling required will depend on the ambient temperature and the altitude. In summary, the altitude and ambient temperature can affect the contactor's performance. At higher altitudes and ambient temperatures, it may be necessary to direct the contactor's current rating. Additional cooling may also be required. The manufacturer's data sheets and the applicable electrical code should be consulted to determine the appropriate directing factors and cooling requirements. The type of enclosure in which the contactor is installed can also affect its performance. The enclosure protects the contactor from environmental factors such as dust, moisture, and corrosion. The enclosure also provides a degree of safety by preventing accidental contact with live parts. There are various types of enclosures available, each with a different level of protection. The National Electrical Manufacturers Association (NEMA) defines the standards for enclosures. NEMA enclosure types are classified by their ability to protect against specific environmental conditions. For example, a NEMA Type 1 enclosure provides protection against dust and light. A NEMA Type 3R enclosure provides protection against rain and ice. A NEMA Type 4 enclosure provides protection against water and dust. A NEMA Type 4X enclosure provides protection against water, dust, and corrosion. The selection of the appropriate enclosure type depends on the specific environmental conditions in which the contactor will be operating. For example, if the contactor will be installed in a dusty environment, a NEMA Type 12 enclosure may be required. If the contactor will be installed in a wet environment, a NEMA Type 4 or 4X enclosure may be required. In addition to NEMA enclosure types, there are also International Protection (IP) enclosure types. IP enclosure types are classified by their ability to protect against dust and water. For example, an I-65 enclosure provides protection against dust and water jets. An I-67 enclosure provides protection against dust and immersion in water. The selection of the appropriate IP enclosure type depends on the specific environmental conditions in which the contactor will be operating. It is important to ensure that the enclosure is properly installed and sealed to maintain its protective properties. The enclosure should be inspected regularly for signs of damage or deterioration. Any damage should be repaired promptly to prevent environmental factors from affecting the contactor's performance. In summary, the type of enclosure can affect the contactor's performance. The enclosure protects the contactor from environmental factors and provides a degree of safety. The selection of the appropriate enclosure type depends on the specific environmental conditions in which the contactor will be operating. The enclosure should be properly installed and maintained to ensure its protective properties.